Hello everybody, welcome back to another lesson on sequences and series. Today we are going to be looking at infinite series. Before I get to the theory portion of today's lesson, I'm going to ask you a question. Have you ever thought about if there's a possibility of adding an infinite amount of terms in a pattern together? So if there's a pattern that goes on and on and on, it's just a pattern that's an infinite amount of terms, what would actually happen if I added those values together, and would it be possible to actually say if I add an infinite amount together, it's going to be equal to one specific number? Well, today we're going to have a look at that. It may not seem possible, but it's possible. We're going to do it together. Let's look at the next slide. So for today, we are going to first look at the concept of a series that diverges and a series that converges. Using that information, we're going to make a conclusion about what type of series I'm allowed to calculate a sum to infinity to. So let's have a look at the first definition, which is a series that converges, or a series that converge. When a series converges, so this word is important, it means that the terms approach zero. So as the terms of the pattern go on and on, they get closer and closer to zero. And a series that converges, the sum approaches a specific number. So the terms themselves become smaller and smaller and closer to zero, and the series of this convergent pattern approaches a specific number. So let's look at how I could actually try and illustrate that. So if I give you a specific geometric sequence where A is 2 and R is a half. So I've given you that the first term is 2 and the ratio is a half. The sequence will go in the following manner. It's going to go 2, 1, a half, a quarter, an eighth, a 16th, 1 over 32, 1 over 64. I'm sure that everyone is agreeing with me that these fractions are getting smaller and smaller. We know that nobody wants 1/64th of a cake. We want half a cake or a quarter of a cake. If I then come and say you're going to have 1 over 28th of a cake, no one's going to be happy with that. But if these fractions continue on and on, they're going to get closer to 0. So we can see that the fractions are becoming increasingly smaller, so we can say that the terms of the sequence are approaching 0. So using this same example, we know that the series is when I add the values of a sequence together. So the series will be 2 plus 1 plus a half plus a quarter going on. So just a reminder, we said that a series that is convergent, the terms itself get closer and closer to 0, but the sum approaches a certain number. So if I take the first few terms and I add 2 plus 1 plus a half plus a quarter, I get 3,75. So I can kind of see that this number is fairly close to 4. But now I'm going to see what happens if I continue to add terms of this specific sequence together. Then if I add a few more portions of this series together, with 2 plus 1 plus a half going the whole way up to a 16th, I get 3,9375. So I'm sure that you guys can see that actually the sum of this series is starting to head towards the number 4. Let's add the values from 2 going the whole way up to 1 over 64. If I added all of those together, you can test it on your calculators, I'm going to get 3,984375. I'm sure that you guys will all agree with me that this sum is approaching the value of 4. So everyone, as the terms themselves, as they went on and on and on, the terms became closer and closer to 0. But the sum of these terms continue to become closer and closer to 4. Because these two properties have been met, we can say that the series is converging. Let's look what a diverging series is. So, series that diverge. When a series diverges, it means that their terms do not approach 0 and their sum does not approach a specific number. So it's essentially the complete opposite of a series that converges. So an example of a series that diverges, if you are given the series Tn is equal to 2n plus 1, the series, or the sequence rather, will be 3, 5, 7, going on, and I'm sure you guys can see that the numbers are getting bigger. They're not getting smaller, so the terms are not approaching 0. Whereas the example before, the terms were approaching 0. The series would be 3 plus 5 plus 7 going the whole way up to plus 15. This sum is not approaching a specific example or a specific number. Before, our series was approaching the number 4. So, everybody, I hope that you can see, because the term values are not approaching 0 and that the sum is not approaching a specific number, this series is diverging. Let's look at the next slide. Please, can you just note, the next example is essentially saying that if we have a ratio that's less than -1 or a ratio that's bigger than 1, the series will diverge. In the next example, we can see that if A is 2 and if R is -3, the sequence will be 2, -6, 18, -54, going on. Again, the terms are not approaching 0. The series would be 2 minus 6 plus 18 going the whole way up to plus 486 or minus 486. This sum is not approaching a specific number. So again, guys, because the terms are not approaching 0 and the sum is not approaching a specific number, this series is diverging. After the break, we'll define sum to infinity.